Hello there, Aria. Just looks like it's you and me today. Oh, and Camille, there we go. What's up, everybody? Sorry I'm 2 minutes late. I'm in a new location with a new desk, new paintings. Hope you guys like the new setup. It's only for 2 days, and then I'm back to normal. Look at that. How's everyone's weekend? Again, static. Weekend was static. As a dynamic, that's not a bad thing, I guess. Does that mean just a lot of sitting around? HBU. Wish I knew what HBU meant. How about you? Thank you. My weekend was fantastic. It was my friend's birthday, and we did birthday things. Static. Hey, static is at least some noise, and I love making noise. So thank you for making noise. So you partied. I would say you should interpret birthday things to mean whatever you want it to mean, but I don't know. Like I don't know what you interpret birthday things to mean. I don't know how messed up your minds are. What you guys think I did? But let's just leave it up. We just did birthday thing. We said happy birthday. We didn't sing it. We said it because he doesn't like singing. We had a cake. The whole 9 yards. Also, nothing else. Yeah, that was it. My weekend was pretty static too. But anyway, welcome back to Discrete Math. This is week 2. Last week we did a welcome video, which I enjoyed very much, and then we did sections 2.1, and then today we're going to start section 2.2. I feel like you were getting lit. Why did I read that out loud? I could just pretend I wasn't looking at the chat. Anyway, the chat's blowing up. Look at this. Anyway, I'm going to go ahead and do what I always do when I run into a problem, and that is start doing math. I should, like physical stress, I stress math. It doesn't make you skinny, but it does make you weird to talk to, I guess. There's a lot of math in my head. But anyway, let's get started. So I am going to share my second camera. All right. So enough about me, about math. You guys had a chance to talk about yourselves and you didn't, so I'm going to do math. This is your punishment for not talking. It's math. Just kidding. Math's never a punishment. It's amazing. So last time, the very end of class, well, actually the very end was tautologies and contradictions, but before that, we talked about all these laws. I wrote down, there we go. I wrote down some of the non-obvious ones here. We have the commutative law, and commutative, just like with addition and multiplication, just means the operation symmetric, right? P and Q is the same thing as Q and P. P or Q is the same as Q or P. Associative just means you can put parentheses wherever you want between ands and ors. Like saying P and Q and R is the same thing as saying P and Q and R. Same thing with ors. Where it gets interesting, the double negative law is also pretty obvious. The opposite of an opposite is just the original thing, right? For example, if it was opposite day, right, but also it was like opposite year, they would cancel out, and then it would just be a normal day. But anyway, then the distributive law and De Morgan's law are the two interesting ones. These are the two ones that aren't entirely obvious. And these are saying that P and Q or R, that's logically equivalent to P and Q or P and R. And so what you do is you distribute the P and to the Q, and you distribute the P and to the R, and you keep that or in the middle right there. And then De Morgan's laws just say if you have a little negation sign out in front of a P and Q, you can distribute the negation to both of them. You put it on. Anyway, we went over this last time. These are the laws, and these are all proven from truth tables. We know they're true because of truth tables.
Professor, I had a question.
Well, I think we're gonna end up there. No, we don't just, first of all, I don't like the word laws, because laws implies we made them up. We did not make these up. The only thing we made up, the only thing this assumes is that things are true and false. Once you assume things are true and false, these things work. Yes, Afra, what's going on?
In the quizzes, we had one of the questions where we asked to identify the situation, and there was another law that's called negation law. Is the double negative law and the negation law same?
Yes, I'm sorry. Yes, they are. Yes. Yeah. Yes. No questions aren't that interesting, are they? It's just yes or no. Yeah. No. I think I labeled it here double negative law because I think it makes more sense to say it like that. But in the quiz, I forgot to go back and change it to what we said in class. But yeah, that's just the negation law. Anyway, so yes, these are all the laws we did. You like my That's like Batman. Like when you have to change between a scene, that's what I do. Anyway, so these are laws. We didn't just do them for no reason, though. We did them because they're very, very, very useful to identify when two logical expressions are true, even if they don't look true at all necessarily. But we're going to get that in a second. Let's just talk about how we can use these laws to say things about other things. So, for example, let's check out this logical expression right here. Logical expression is not P and not Q or R. All right? There we go. So this is a logical expression. Maybe I should say somewhere, assume P, Q, and R are statements. Because remember, the ands and the ors, they're operations on statements. So that's all it means. So assume P, Q, and R are statements, and then we have this expression right here. And then, well, let's see. Is there any way that we can rewrite this expression using the laws we have right here? What do you guys think? Well, I'll tell you this. There's always an easy one. We could always say that this is equivalent to not P and not Q or not R, right? That's just the double negative law or the negation law, all right? We can always do that. That's easy. Or let's see, is there another law that applies to what we have here?
Could we do a distributive?
Yeah, absolutely, right? This looks like a distributive. I mean, like, don't get caught up on the P's and Q's here. These are just like variables. They're just like, imagine computer science, right? When you define a variable for your method or your function, right? These are just variables. But if we think about like not P and not Q being their own statements, which they are, you say, okay, this is one statement and a statement or R, right? And so that's totally where the distributive law applies. So we can also say this is equivalent to not P. Using the distributive law, right? We distribute the not P and to the not Q, right? And then we also distribute it to the not R. And I put way more parentheses than you need. You never need that. Because we know the order of operations, so we don't need to do all that. And that's just to be a not P and, right? Because you're distributing the and. So you distribute the and, but the thing between these two statements is still the or. So that's what was in the parentheses. But that's just how the distributive law works. So you got to think about it that way, just memorize the distributive law. So we got that. Is there anything else we can do with this? I don't think so. I think we're good there. I'm not going to let you mull that over. Oh, do we have an option? Do we have an option? Good question. Can we factor out a not for the entire equation and then use De Morgan's law? So the question here is, does this equal, put it in purple because it's a question. Even though I don't want to use purple because there's no question. I love the color purple. But anyway, the question is this equivalent to not P and not Q or R? Is that true? Well, let's do maybe a smaller example to see if that even makes any sense. Like what if what if we had instead, this is going to be an aside, what if we had not P and Q? Is that the same thing as not P and Q? Is that what you're asking? So, well, first of all, I never said favorite color. I said it's a great color. If you can guess my favorite color, no extra points, but I will raise my hand in the chat and you can raise your hand at the same time. It's like we did a high five. Anyway, so is this true right here? Well, how can we find out if a logical equation is true? A logical equivalence is true. Who's got me? We wrote this out last time. How can we tell? Like, how can we tell? Like, do we have to guess? Like, how can we prove that this is true or not true? TT, truth table, exactly, right? This all comes down to truth table, so we can always use truth table to prove it. So let's make a truth table real quick. We'll have a P and a Q, and then we'll have a not P, and then we'll have a not P and Q, and then finally over here we'll have a not P and Q like that. Is all this true? So remember the cases are true. We had to check the cases true, 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 false, false, true, and false, false. Look at those lines. There we go. So let's just do it. So if P is true, not P is false. And then we're in the case where P is true and Q is true. So then not P and Q would be, well, that would be false, right? Because it's not true that both not P and Q are true because not P is false. Then over here we have not P and Q. So here P and Q is true. So that means not P and Q is false. And then right here, in the case where P is true and Q is false, well, not P is false. Not P and Q is going to also be false because neither not P or Q is true. And then not P and Q, well, P and Q here, that's false. It's not true that P and Q are true. So P and Q is false. So the negation of P and Q must be true. Notice false does not equal true here. So we have to go any further. We've proven that these two expressions will not always give you the same truth value if you have for any values of P and Q. Specifically, if P is true and Q is false, they will not give you the same truth value. Meaning these two things are not the same thing. The point of that is you can't just kind of take out a negation from the whole thing like that. It doesn't quite work that way. Yeah, good. So, oh no. Where's my washcloth thingy? Oh well. Luckily, as a mathematician, I've evolved a washcloth connected to my arm. So anyway, so yeah, so we can't just pull it out. But I think that's about all the interesting things we can do with this original first thing here. But how about here? Can we keep going here? Can we do anything with these guys? Well, oh yes, this is not true. So we're not going to put that. We just showed that wasn't going to work. But yeah, I mean, yeah. Is there anything we can do with this expression right here? Let's look at the laws again. These are the laws we have. So let's see, the commutative law. I mean, we could do the commutative law. We could always do that, right? I mean, we could write this as not Q and not P, or not P and R, right? That's using the commutative law. We could always do that. That's not entirely that interesting. We can do it, right? I mean, we could do the commutative law up here too. We could call this not P and not R or not Q, right? We could always use the commutative law. By the way, this is not going anywhere. If you guys are like, did I miss where this is going? It's not going anywhere right now. I'm just showing you what you can do. I mean, we have these expressions. I'm saying this expression is equivalent to this expression, which is equivalent to that expression. What does that look like on this sheet right here?
Not P.
What do you say?
We can take the not out, right? And we have P R, what was the R? Yeah, P R Q.
Someone in the chat said De Morgan's law, and you said take the not out. The same thing. That's exactly what we're talking about here, right? This looks a lot like that right there, right? Which by De Morgan's law is equivalent to that. We can take the not out and flip the little sign in the middle. So this right here is equivalent to not P or Q, or not P and R, right? The point is that this is equivalent to this, which is equivalent to this. This is equivalent to this, which is equivalent to this, which is equivalent to this. These are all equivalent to each other. We can use these laws to rewrite logical expressions in a bunch of different ways. Which you might say, well, what's the point of that? What's the point of rewriting something? Well, sometimes one way might be a lot easier. One way might be a very useful theorem or something like that. One way might be confusing, you might not know what it means. But the other way you see it like that, go, oh my God, that makes a lot of sense. Like this is a really important fact, right? The point is these are logically equivalent. These are logically equivalent expressions. So if this is true, that means this is true. So later on the line, if we're trying to prove something true, right? Like let's say you're tasked with proving this true, but you find it's easier to prove this true. Well, it's the same thing. Like proving this true is the same as proving this true because they're literally the same logical expression, just rewritten. Hope that makes sense. So we're not going to quite prove anything yet, but what we are going to do is let's look at how we would write up a proof of a logical equivalence. So I just kind of did a bunch of logical equivalence here. I kind of just did it a little casual, a little loose. Let's see how you would formally write up a logical equivalence. So let's say we wanted to prove so if I asked you to prove that P and Q and R or S negated is equivalent to what was it? Not P or not Q or not R and not S, right? Let's say we want to prove this to be true, right? This is what we're after. How can we show that's true? Well, first thing you do when you're going to prove this class is you first just write down the words proof. Just like that, lets everyone know, hey, we're doing a proof. Next thing you do is you start with the things you know. So actually, we don't really know. Okay. So this is the thing we want to prove, right? And so what I'm going to do is I'm going to start with the left side, and then through a chain of logical equivalences, show that this is equivalent to the right side. You could also start with the right side and then show it through a chain of logical equivalences that it equals the left side. Doesn't matter. If I'm going to do the left side, why is it out of focus? Jiggle that. That's in focus. Oh. There we go. So, how can we prove this true? So I'm going to say, so remember, we're not trying to prove that the left side or the right side as a statement is true. We're trying to prove this equivalence true, right? So remember, this is a statement. The left side and the right side are statements. I mean, they're a combination of statements, but a combination of statements is itself a statement. But we're not trying to prove the right or left side true. We're trying to prove this whole thing true, meaning no matter what P, Q, R, and S are, the whole thing's going to be true. So I keep adding caveats. Let's just do it. Let's just do it. So to prove this true, we can start off with the left side. And we can say that not P and Q and R or S is equivalent to what? Remember our laws we got here. So all these laws, what's it look like we can do? Which law can we use? I can smile all day. I mean, what's it look like, right? I mean, at the end of the day here, right, we have P and Q and R. This is in parentheses. This is kind of its own statement. I mean, you can call it T if you want. Like, this is its own thing. Actually, T is probably not good because T means true. Let's call it U. Interesting. And then, or S. And then on the outside, we have a not. So what's it look like? Thank you very much. De Morgan's law, right? This is De Morgan's law again. This is a statement or another statement, and you're negating the whole thing. So we can use De Morgan's law to say, in that case, we can kind of distribute the negative to both the interior statements and then flip the sign in the middle. So this is going to be equivalent to not P and Q and R or not S by De Morgan's law. All right. So we're, oh wait, sorry, this should be an and right here, right? Because the word is like you flip the sign in the middle. There we go. So, and now we're closer to this, but these have a bunch of little tilde negation things on the inside. This has on the outside. So we're not done yet, but we're a little bit closer. Can we maybe rewrite this to get closer to that? What laws do we have at our disposal again?
Distributive laws.
Distributive laws. Can we use distributive laws? So distributive laws happen when you have like an and. Oh, I see what you're saying. So distributive laws happen when you have an and then you have a Q or R. It's kind of where you start mixing symbols a little bit. Because you have an and here and like an or here. But here, if you're looking at this right here, it's just an and. We don't have like an and or, right? But, this is a tricky one. Because I think what we want to do is we want to say, oh, let's distribute this tilde, right? If we distribute this tilde, right? We know about De Morgan's law, it should flip the signs in the middle. And then we'll get not P or not Q or not R just like we wanted. But nowhere on this list of laws do we have this working with three statements on the interior like that. Right? We had De Morgan's law with 2 statements on the interior. We basically want to do this law right here, but with 3 statements. But we don't have that written, meaning we haven't proven it. Right? All of these are proven from truth tables. The fact that this equals this, which I think is true, has not been proven from a truth table. We could prove from a truth table, or maybe we could use some laws in a clever way and avoid the truth table. Well, notice. Like I said, if this was 2 statements in here instead of 3, we could just use distributive law, or whatever, and we're all good. De Morgan's law, we're all good. Well, let me ask you this. P implies Q implies R, or P and Q and R. I mean, is that any different from P and Q and R, or P and Q and R? No. This is exactly what the associative law here says. The associative law says no matter what order, right, you put these parentheses in. So whether you do P and Q first and then tack on the R, or if you do P first and then you tack on the and Q and R, you get the same thing, right? We can think of P and Q as its own statement. So we can think of P and Q as its own statement, and then we're doing an and R. And this is by associative law, which tells us it does not matter, right, if we do P and Q first or we do Q and R first, because here it doesn't specify. The associative law says that doesn't matter. So now we think of P and Q as its own statement, which it is. But then we have a statement and a negation on the outside, so we can use De Morgan's law. So then this becomes not, this becomes not P and Q and not R. We still have the and not S. And we did that by De Morgan's law again. I'm sorry. We actually wanted a or here. That's right. Because De Morgan's law, you do the tilde and then it flips a sign in the middle. I always forget that. But anyway, so we have that right there. So we have that not P and Q or not R. Well, then what can we do with this last little bit right here? This last little bit, I'm not going to make you say it again. That's just De Morgan's law again. Because remember, we have a not with a thing in front of parentheses, or with two statements in parentheses connected by an and, meaning we can just flip that and to an or and distribute that negation to both of them. So this is going to be not P, flip that symbol in the middle, or not Q, or not R, and not S. We just tack that on. What we did happens right here. By De Morgan's law again. And then finally, to get what we want it to look like, we say, okay, we're doing the not P or the not Q, and then having the or not R. But by the associative law, the order doesn't matter. So this is just not P or not Q or not R and not S by associative law. And notice this is exactly what we wanted to get right here. So we started from here, and then by applying the right laws, we ended up here. So we start from here and show this is logically equivalent to this, which is logically equivalent to this, which is logically equivalent to this, equivalent to this, equivalent to this. Meaning this and this must be logically equivalent. So therefore, not P and Q and R or S is logically equivalent to not P or not Q or not R and not S. They could put a little square to mean you're done with the proof. So this is our first real proof we kind of see in the class. And this is how you do it for these logical equivalences. You can always just I'm not even telling you what you can do. It's like, this isn't me saying this is not me saying you're not allowed to do this. You can do this. I'm just saying that it is true. It is true that this is equivalent to this by De Morgan's law. De Morgan's law proves this to be true. Associative law proves that to be true. That proves that to be true. And so you go down till you get to the end. Any questions on why this works? Cool. So in the homework of the test, that probably means I said way too much. So in the homework of the test, always write it like this. And the part that's important is this part right here. You need to explain why it's true, right? So every step you go on the way, you need to say why it's true. And why it's true is by De Morgan's law, by associative law, by De Morgan's law, by De Morgan's law, by associative law. Always include this on the side. I mean, this is just like, we don't need to go over that. But anyway, yeah. So this is how you prove it. Is there any other way we could have proven this statement? TT again, yeah. I said last time that the way you prove logical statements, logical equivalence is true is with truth tables. And that's true. I wasn't lying to you. That's still true, right? You can prove this with a truth table. Why wouldn't we? Well, let's check it out. We wouldn't want to prove that true because, or we want to prove this truth table because if we did this, we'd have a P, Q, R, and S. We need to eventually prove that this statement and this statement, these two statements, give the same truth values for any possible inputs of P, Q, R, and S. But what are the possible inputs of P, Q, R, and S? Well, P could be true, Q could be true, R could be true, S could be true. P could be true, Q could be true, R could be true, S could be false. P could be true, Q could be true, R could be false, S could be true. P could be true, Q could be true, R could be false. S could be false. P could be true, Q could be false, R could be true, S could be true. Do you see how many of these we're going to need to cover everything? And then for each one of these, we're going to need to go through and figure all that out. This is becoming one of my favorite words, which is untenable. Untenable is a great word because it doesn't mean impossible. We could do it, but we're lazy, right? It's like, come on, like don't expect us to do that, right? This would be what, 16 rows, right? So to do the 4 of 16. Yeah, so we need 16 rows of the truth table. It's going to be a whole thing. Don't worry about it. That's the exact beauty of these laws. These laws do some very important truth tables for us already, and then we can just combine them, we can just use them together cleverly to prove bigger equivalences like this are true. But it also comes down to the truth table, because in that little thing I had right there where I said by distributive law, by this, by that, by that, each of those by distributive law, if you ask why the distributive law works, well, there's a truth table that shows that works. If you ask why the associative law works, there's a truth table for that. But anyway, I mean, this is exactly what math is. We start with the truth tables, we build up equivalences. That lets us build up more complicated equivalences, lets us build theorems, we can build more theorems off that, and it just builds and builds and builds and builds and builds like the most beautiful, beautiful snow rolling down a hill you could possibly find. Anyway, any questions on that? Okay, so let's now talk about, what time is it, first of all? What's going on? Where's my, okay, we got some time, perfect. So now, let's talk about how to use that's all crooked. That's less crooked. There we go. How to use logical operations to prove things about their inputs. I'll say how to use maybe the results. So far, we've just kind of been, so far we have not worried, like all of these laws, right? All of these laws, that equivalence you just did, truth tables, all of that, it never really concerns itself with what the value of P and Q is. It just says it works for any value of P and Q and moves on. But now we're going to talk about how to actually prove if the P and Q statements are true and false given certain information. So let's say we're given P and Q are true. Given P or Q is true and P false, what can we say about Q? Well, people, put your Sherlock Holmes hat on, right? Smoke a candy pipe. I don't know if they make, I don't know that candy pipes, you know what I mean? Like, what can we say about Q, given P or Q is true and P is false? Because P or Q is true, what's that mean? Oh, we got something in the chat. We got something brewing. True. Yeah. Yeah. We can say that Q is true.
True.
So say something? Or was that an accidental unmuting that just happened? Okay, so given P or Q is true and P is false, what can we say about Q? We can say Q is true. Claim Q is true. Proof. How can we prove that? Well, we could say since P or Q is equivalent to true, by truth table for or, one of P or Q is true. Because P is false, or maybe I'll put it this way. P equals true or Q equals true. Because P is false, Q must be true. Done. I mean, this is kind of like, this feels like we're talking in circles here. But all we're saying is that by the truth table for P or Q, if you look at that truth table, you see that you get true only in the rows where one of P or Q is true. And since Q is false, that means the other one must be true. Otherwise, in a situation where it's false, false, and P or Q would be false. We know P or Q is not false because we're given it's true. That's all we're saying. I mean, this is like saying, like, let's say, for example, you know that, like, you know, based on your Netflix history, that your brother either watched, I don't know, what's on Netflix, either watched Stranger Things or watched Love Actually, right? But you also know, based on your brother's love life, he probably didn't watch Love Actually, therefore he must have watched Stranger Things. Something like that. You see what I'm saying? So that is how you can prove things about statements based on the logical operations. Hope this makes sense. And we can also say, there we go. For example, given P and Q false and P true, then what must happen? Q must be false. Exactly, right? Q must be false because if P and Q is false, right? That means one of them must not be true. Because P is true, the other one, Q, must be false. I can do that proof. That's how it works. But you guys see the point that knowing things about this combined statement, right, can let us know things about the constituent statements that went into it. Hope that makes sense. All right. Now that was all just lead up to a very, very important part of this whole class. This is like the nucleus for like 1,000 different things we're going to do in the coming exciting weeks, which will turn into months, which if you decide to dedicate your life to math on the spot will turn into years. And then if you actually prove something, your legacy will last forever. So this could be the beginning of forever right here. Let's say, or this is called conditional statements. Wow, could I be any not neater? That's my impression of Matthew Perry doing math. Conditional statements. So let's define a new binary operation. We're going to define it in the following way. We're going to call it, actually, I'm not going to give it a name yet. But it takes in a PRQ. I don't want to give it the names. I don't want to give away what it is yet. It's going to take in a PRQ, and then I'm going to define it with a truth table. And so we have P, Q, and then we have P arrow Q. So the symbol for this binary operation is going to be an arrow. Like remember, and is this, or is this, XOR is that. The symbol for this is going to be this arrow right here. And we have to define it for the case where P is true, Q is true, P is true, Q is false, P is false, Q is true, P is false, Q is false. To define for all these situations. And here's how it's defined. If P and Q are true, we're going to say P arrow Q here is true. If P is true and Q is false, we're going to say P arrow Q is false. If P is false and Q is true, we're going to say P arrow Q is true. If P is false and Q is false, we're going to say P arrow Q is also true. So this is definition. And I should say, by the way, this whole like putting these curly braces and making it look like a function, this is not standard math notation. I'm just doing it for the class. Standard math notation would just be the truth table. It wouldn't worry about the rest of it. But I'm putting the function stuff there to let you guys know that this is like a function we're looking at here. It has an input and output. The inputs are P and Q. The output is the truth value of P arrow Q. So what the heck does it look like this function's doing? Like if we needed to comment our code here, right? If we needed to comment our code and write what this function does, what would we say it does? I'd help if you can see it. This is a new webcam. We're gonna get the kinks worked out. You got this webcam. There you go. So what's it look like it does? How'd you describe it? No wrong answers necessarily. I can literally hear crickets outside. I don't know if you guys knew that. Nothing? What do we got? What do we got here? Ooh, P implies Q. Someone's been reading the head. So P implies, so that's very true. P implies Q. But P implies Q, what's that mean? So what this seems to do is this operation, I like the way I wrote it. returns true whenever, in the case, in cases where Q happens whenever P happens. So this operation turns true whenever Q happens, or where in a case where Q happens whenever P happens. Or another way you can put that is if P, then, or in the case where Q happens or P happens is true. Or you can say if P, then Q is true. So this might seem weird. Let's break it down. So in this first case here, P is true and then Q is true. So we're saying Q happens or P happens. Well, okay, actually, maybe I should say by happens, I mean is true. Q is true whenever P is true. So is it true that Q happens, or Q is true whenever P is true? Well, here P is true and Q turned out to be true, and so it's true. In this case, P was true, but Q was not true. Q was false. So it was not true that whenever P happened, Q happened. And that's why it's a false here, right? This is a very weird thing to think about. Remember that like P and Q returns true when P is true and Q is true, right? That's the way you can describe it in English. The way you define it is with the truth table, but you can describe it in English like that. In English, we describe this operation as we say this returns true when Q follows from P, when Q is true whenever P is true. So in this next case, well, P is not true. And so the idea of Q is true whenever P is true, well, it doesn't matter, right? Because P is not true. And so we call it true because it didn't fail, right? Same thing out here. P is false, right? P is false. And so Q is true whenever P is true. Well, this only really concerns itself with the case where P is true. So this is, it doesn't fail this criteria, right? And so this is going to make a lot more sense when we do more examples and stuff like that. But what I'm going to call this is the if-then function, right? And I call it the if-then function, P and Q, and it spits out true as long as P is true, or as long as Q follows from P. Another way to put it. So here's what I'll say. Here's what I'll write down for your notes and stuff like that. If P and Q are statements, P implies Q is another statement, right? Just like how P and Q or P or Q is a statement. So P implies Q is another statement. And then the way you read it out loud is P implies Q, right? And yeah. And then P implies Q is true if whenever, in all cases, where Q or P is true Q is also true. Returns false otherwise. So, I hope saying it 5,000 different ways and starting to make it seep in a little bit. So this P implies Q, it is a statement, right? And it's basically an if-then statement. It's saying P implies Q is true, means that if P happened, then Q must also, if P is true, then Q must also be true. What's our time here? What do we got? Yeah. So, yes. So I'll say, yeah, any questions on this? This is kind of confusing. We're gonna do some examples. We're not nearly leaving it here. Yes, there's a question of if we could possibly explain it again because it's confusing, and you're totally right. It is confusing. So this is the definition of what P implies Q means. Theoretically, this is all you need to know. But I'm trying to explain it in English because this idea of an if-then statement is a lot older than the idea of truth tables. People were working with if-thens before they even thought of the idea of truth tables. So let's just do some examples. Let's do some examples. And then it'll work out. So, all right. Let's say so the statement I'll make, it'll be a conditional statement. Conditional statements are just if-then statements. Oops. Conditional statement is what that says. Might be if the Earth explodes, I will not be in good shape, physically or financially. If the Earth explodes, I will not be in good shape. This is an if-then statement. This right here, you can call P, and this right here is like Q. We have a P and a Q. In this case, it is true. This statement right here, this statement does in fact equal true. Why is this statement true? Well, let's check it out. And if then is true, right? Based on that truth table, I'll write it again. Yeah, write it again. So actually, I'll say this is the same thing as saying P implies Q. In this case, it's true. Because remember, an if then is true as long as whenever P is true, Q is true. So we have that. Yeah, so let's check it out. If the Earth explodes, will I be in bad shape? Yes, I will be in bad shape. This is totally a true if then, right? And so in the case, so P and Q But if, sorry. So in the case where P is true, in the case where the Earth does explode, what's Q gonna be? So in the case where the Earth does explode, what kind of shape will I be in? Will I be in bad shape?
Yeah, you'll be in bad shape.
I'll be in pretty bad shape. I'll be pretty banged up, right? I'll be worse for wear, is how you could put it, right? If my gravestone would say, here lies Daniel, he's worse for wear. Okay, so if they're exposed, I'll be in bad shape. So in the case where P is true, Q must be true, right? They go together. So in the case P is true, Q must be true. And so we're here, right? So that matches up. In the case where P is false, right? If the Earth doesn't explode, sorry. Let's view it like this. There are a couple options here, Which one of these can be true? Which of the following can be true simultaneously? And I'll say one. The Earth explodes. I am in bad shape. 2. The Earth explodes. I am in good shape. 3. The Earth does not explode. I am in bad shape. And 4, the Earth does not explode, and I am in good shape. Notice, by the way, this is P, this is P, this is Q, this is not Q, this is not P, this is regular Q, this is not P, and this is regular Q. All right, so which of the following can be true simultaneously? Can number 1 happen? Can the Earth explode and I can be in bad shape?
Yeah.
Yeah. If the Earth explodes, I'll probably be in bad shape. Let's use blue. How about number 2? Can the Earth explode and I be in good shape? Like if it happened right now?
Nope.
No, it's not going to be good. How about, so I'll circle that. There's not even going to circle. How about 3? Could that happen? Could the Earth not explode and I be in bad shape?
Yes.
It's possible, right? The Earth could not explode, but I mean, I could be devastated by a spotty valve, right? And so, this could happen. How about this? Could the Earth not explode and I be in good shape?
Yes.
That could also happen. That's what I am right now. So, notice if P is the Earth explodes and Q is I am in bad shape, that these are the following that can happen simultaneously, right? And that's exactly what's going on with this truth table. That's exactly what it means for P implies Q to be true, is that these things could be true, right? And the one thing that can't happen is that P could happen and then not Q. That's the one thing that can't happen, because then that means if P, then this if statement is not true. So the fact that if the Earth explodes, I will not be in good shape, it's true. This is true because these are our options. Because whenever the Earth explodes, I will not be in good shape. right? That's all it means. All this means, all P implies Q means is that if P happens, then Q must happen. If P doesn't happen, then Q can do whatever you want. So,
Professor, in the fourth statement at the second part, is it also not Q because it says in good shape?
you're totally right. You're totally right. Totally right. Thank you very much. This is the equivalent of false false down here. Yeah. So let's write that down, and that'll be a good place to stop, and we'll pick up tomorrow. So P implies Q, true, means if P, then Q. That's it. P implies Q, it's an if statement. It means, and you can say it like that. You can say P implies Q, or you can say if P, then Q, right? It's a statement. And so if P, then Q, that's a statement. You can think of a lot of if P, then Q. And so for example, if my computer crashes, then this Zoom call ends, right? This is an if statement. Is this true or false?
True.
That times I just say it's true.
True.
Since whenever P equals true, Q equals true. How about this statement? If X is even, then X plus 1 is odd. Is this true?
Yeah.
Yeah, right? If you have an even number and you add 1, you get an odd number. So this is true. For the same reason, because whenever P is true, whenever X is even, X plus 1 is odd. That's all it's saying. And then how about this? If X squared is positive, then X is positive.
False.
Yes. This is false. This is false since if X equals -2, X squared would be -2 squared, which equals +4. So P is true, but Q is false. So here, in the case where X equals -2, P is true, but Q is false. So it's not true that whenever P is true, Q is false. And in the truth table, we have true, true, false, false, true, false, true, false, true, false, true, true. In the truth table, you're here. You're in the case where P is true and Q is false. And that means P implies Q should output false. Exactly what we said it does. So that's how if-then statements relate to this truth table. We're way over time, but that is it. Any questions before we leave? Is the if-then making more sense now?
Yeah, the examples made it a little better.
Yeah, right? It's a confusing thing because it's weird to think about if-then as a statement itself because you think of it as relating to statements, but it is a statement itself. If-then is a statement. It's either true or false. And this if-then is true, this if-then is true, this if-then is false. All right, well, that's class. Stop recording. Everything now is